Hyperparameter search should not waste full runs on doomed settings. Optuna prunes bad XGBoost trials while the search is still running. This is the setup you'll be able to run after this, which tunes a boosted tree model and prunes weak trials early to speed up the search. I'm Professor Pi, teaching AI foundations with simple Python. Tuning boosted trees is a common pain in applied projects. You run many full trainings and wait, and most settings turn out to be worse than you hoped. Optuna helps by running smart trials and stopping the losers early. That saves time and lets you explore more candidates for the same compute budget. At a high level, we want two things. First, a clear metric that reflects the model goal. Here we use AUC, the area under the receiver operating characteristic curve, which measures ranking quality between classes. Second, an optimizer that proposes parameter values and prunes slow or underperforming trials. N estimators is the number of trees, and learning rate controls step size. These two often trade off. We will build a short pipeline, a quick baseline model, a small Optuna sweep over learning rate, then add pruning, then try a sampler that models correlated parameters, and finally assemble the tune settings into a final model. This keeps each step focused and makes the code easier to follow. Now we'll create a quick baseline to see how a simple model performs. This snippet trains a quick XGBoost baseline and measures AUC on a holdout set. We generate a small classification dataset and split it into training and validation sets for a clean signal. The XGBClassifier builds trees with a modest depth and uses early stopping to avoid overfitting while training. After fitting, predict proba gives class probabilities, and rock AUC score summarizes ranking quality on the validation labels. Increasing N estimators can help if early stopping rounds is set. Without it, more trees may overfit and degrade validation AUC. The printed baseline AUC shows how well a simple untuned model separates classes and sets a reference. Next, we'll run a focused Optuna search for learning rate to improve that baseline. This example starts Optuna hypertuning search to improve the XGBoost model. The objective function builds an XGBClassifier, while Optuna's trial suggests a learning rate from a log-scaled range. We fit on the same training data and return the validation AUC via rock AUC underscore. The study uses create study with direction set to maximize and a TPESampler seeded for reproducibility. Then optimize runs a small number of trials. Lower learning rates usually need more trees, but can generalize better. Higher ones train faster, but risk overshooting. The printed best AUC reports the strongest configuration Optuna found so far, and indicates direct gains over the baseline. Now we will add pruning, so slow bad trials stop before wasting the budget. This code adds Optuna pruning, so bad XGBoost trials stop early. Inside the objective, an XGBClassifier trains with eval metrics set to AUC and passes XGBoostPruningCallback, which reports validation 0 AUC each boosting round. The study uses a MedianPruner, which compares intermediate scores against the median of completed trials, and prunes if a trial falls behind, because pruning raises a signal during training. The slowest or clearly losing settings exit quickly and free up budget for better ones. A larger N estimators gives pruning more chances to assess progress. Too few rounds can suppress pruning decisions. The printed best pruned AUC shows the strongest survivor after skipping weak runs. Next, we will try a sampler that models parameter interactions for subsampling choices. This snippet uses Optuna's multivariate TPE to co-tune correlated XGBoost sampling rates. The objective builds an XGB classifier and lets the trial suggest subsample and cull sample by tree, which often interact to control tree diversity and variance. The multivariate is true sampler, models joint parameter relationships, proposing combinations that fit better than tuning each dimension independently. We fit quickly without validation callbacks to keep compute light. Then evaluate AUC on the held-out validation split. Increasing subsample or cull sample can reduce overfitting, but too much randomness may hurt signal. The printed best AUC shows whether correlated sampling choices improved validation performance over earlier searches. Finally, we will train a final model using the picked parameters to see honest performance. This example assembles tuned parameters from Optuna studies and trains a final XGBoost model. We pull learning rate from the first Optuna study and sampling rates from the multivariate search. Then create a fresh train test split. The final XGB classifier fits on the training portion with a higher N estimators to let the chosen learning rate work effectively. We score the model on the untouched test set using ROC AUC score for an honest evaluation. If you decrease N estimators, training is faster, but test AUC may drop. Increasing it can help until overfitting appears. The printed test AUC reflects real-world performance after pruning and focus search. In a real project, this maps to a train pipeline that runs on a larger dataset, and the same pruning logic lets you iterate faster across more parameters and more data without wasting hours on bad trials. Recap: it is Optuna guiding XGBoost and pruning weak runs early to save time. Use it when you need automated hyperparameter search and want to explore more settings within limited compute. Caveat: pruning needs enough boosting rounds to judge progress, or it may not trigger reliably. Next step: run the same flow but tune max depth to see how tree complexity interacts with learning rate and sampling. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.